Okay, we have one lecture left, and in this one we're going to talk about testing or screening. This is really important now given that we're doing so much screening for the coronavirus, or SARS coronavirus 2 as it's called, and we're seeing lots of bizarro information out there. But it's important to know that we can't just trust the test. Tests can be accurate or they can be inaccurate, and the way we define accuracy is based on validity. So if a test is valid, it tests what it was designed to test. Like, for instance, a bathroom scale. When I stand on my bathroom scale in the morning, I'm assuming that it's valid and it's going to test weight and not height. Now, in terms of doing something like a bathroom scale, the way I would test validity, now it depends on what kind of scale it is, but if you have a traditional scale that uses the little balances and the weights, what we used to do in our research studies, I used to actually be a team leader. So my first introduction into being in research, there was a project called CATCH, Child and Adolescent Trial for Cardiovascular Health. It was in the 1980s, late 80s, and what we did was we'd go to these different schools and we'd weigh individuals and take all these other parameters, body parameters, and to calibrate our scale every day, we take this 50-pound block and we calibrate the scale. If it says 50 pounds, it's good. If it didn't, then we'd have to adjust it. So that's how we validated the scale. Reliability means you'll have the same response over and over and over again. So what we're hoping, though, is that now reliability is dependent on how frequently you measure something. So, for instance, you'll have greater reliability if you measure the same participants using the same measure in a shorter duration than a longer duration. And this is more of an issue with, for instance, with paper pencil tests, because over time people will forget or they'll change so that their scores won't be as similar as they were previously. So that's reliability. There's other kinds of reliability. For instance, inter-rater reliability. So inter-rater reliability measures how consistent a rater is. So, for instance, we see like in the Olympic Games where you have people judging, say, figure skaters. So we're hoping that, I don't know if I said this correctly, but we're hoping that the raters, the inter means between, intra means within, so I might have said that wrong. But inter-rater reliability means that different raters will come up with the same score. So, for instance, if we have two individuals rating somebody for figure skating, we often get different scores. And that's some of the intrigue in those sports. And sometimes it's national interest that manifest in those cases. Like in the old days, it used to be the Russian judge would score the Americans lower and the American judge would score the Russians lower. So there wasn't really strong inter-rater reliability. There's a measure we use called the kappa statistic. If you're interested, I have videos on how to do that in my page here on Facebook, on YouTube. Intra-rater reliability looks at reliability in repeated measures by the same individual. So, for instance, in taking blood pressure, you'd hope that the individual taking the measure would be reliable, that she would get the same measure time and time again. Now that, of course, depends again on how close together the measures are made. So, for instance, like if you took my blood pressure one day and I'm totally relaxed, but you took it, 2 weeks later after something devastating happened, my blood pressure would change. So there are factors that can influence reliability. So reliability just means consistency, and validity means that a test tests what it was designed to test, or measures what it was designed to test. Let's talk about sensitivity, specificity, and positive predictive value. So these are, sensitivity and specificity are two qualities of tests, and they're measures of validity. So sensitivity, and I like to discuss this in terms of probability. And what I'm going to do is I'm going to introduce some. I'm going to introduce them by using a tabular form table, and then I'll do it with probability theory. So sensitivity is the probability that one tests positive given one has the disease. This is very important now with the coronavirus, because we're trying to find the most sensitive tests, the ones that would actually be more likely to correctly identify a person who has the disease as disease positive. So they should test positive. Specificity is the probability one tests negative given one does not have the disease. Positive predictive value, which you don't think about this as much when you're dealing with test design, but in public health we think about it a lot. It's the probability that one has the disease given one tests positive, and PPV is used for determining whether we should or should not screen for diseases. Okay, so let's look at some data here, or a typical table. So this is a typical 2x2 table where we have a person's disease status, and the test result. So T plus means they test positive, T negative means they test negative, D plus means that they have the disease, D minus means they don't have the disease. So this is a typical table, and you should be able to complete this table just on some very basic information. So we're going to go through this in a step-by-step process. So this is for disease D, and right now we're looking at 3,560 or 3,560 individuals. And we're given some data. It says the population prevalence of disease D is 700 per 10,000. So that should, just using that information, we should be able to calculate D positive. So D positive is the number of individuals that we expect to have the disease given this prevalence information. So here's how we calculate it. So I said, how many individuals would you expect to have the disease in our sample? So this is out of the 3,560. Well, normally what I would do is if I just had the proportion, I'd multiply the proportion times 3,560, but I have this value per 10,000. So what I do here is I multiply 700, this 700 per 10,000 times 3,560, and then I have to get rid of that 10,000, so I divide it out. I divide by 10,000, and I get 249.2, which is roughly, so this is what I use the symbol for, 249 individuals. So, as I said, if you divide, I mean, like I said, we usually do this in proportions. You can divide 700 by 10,000. You can just get this probability, which is 0.07. So this is the probability of one having a disease. This is so important in determining everything, understanding these probabilities. So if an individual, so let's complete this. If 249 individuals have disease D in our sample, what number of individuals are disease negative? Well, so we can actually just figure that out pretty easily, right? If 249 individuals have the disease, then the difference between 3,560 and 249 would be the number of individuals who don't have the disease. That's 3,311. So again, in filling out these tables, you just have to just work through them and just fill in the blanks based on addition and subtraction. So here's a definition, first definition here, and I already kind of mentioned it before, what sensitivity is. Sensitivity is a probability that one tests positive given one has the disease. And we're going to use this notation here. This is what's called a conditional probability. So this is testing positive condition on one having the disease. So what's after this slash is the condition. That's a conditional probability. So let's assume that the test sensitivity of test R, or the R test, is 0.97. So how many individuals who have the disease would you expect to test positive in our sample? So this is, again, sensitivity. So this is the probability of testing positive given one is disease positive. That means that you have a 97% chance of testing positive given one is disease positive. That means you also have a 3% chance of testing negative given one is disease positive. So that would be a false negative. So this would be like a true positive, and the complement of this is 1 minus this, which is your false negative. Okay, so we had 249 individuals, as you recall, who are disease positive. And if the sensitivity is 0.97, that means 97% of these would test positive. So that's 242. Again, you know, I get rid of these decimal places here and just round it to a whole number of 242. Round it up. So what I'm doing here is if it's 0.5, like this is 0.5, I'll just round it up. So let's look at specificity. So specificity, that's like sensitivity. So let's look at the definition. Again, it's best to look at it in terms of probabilities. Conditional probability. It's a probability that one tests negative given that one does not have the disease. So again, it's probability of testing negative conditioned on one not having disease. Again, so using this notation is important. Let's assume that the test specificity, so I just make these up, right? But that's not the way it's done in reality. Obviously, this is based on a lot of testing, and a lot of experimentation to find out what these values are. So let's assume that the test specificity of test R is 0.92. How many individuals who do not have the disease would you expect to test negative? Well, we know that 3,311 people do not have the disease, and you multiply that by 0.92, and we get 3046 individuals. So let's look at this table, and this is what I typically do in an exam. I'll ask you to complete the table. So we started with this table up here. The only thing I gave you was the total. I gave you sensitivity and specificity and the prevalence, disease prevalence, and using that information, that's enough to complete the table. So we knew that the prevalence of the disease was 7%, right? 0.07. So we multiplied 0.07 times 3,560, and we got 249. And 3,560 minus 249 is 3,311. So we got that. We know that 249 individuals have the disease, and we multiplied it by the sensitivity, so it's a probability of testing positive given one is disease positive, that's 242. 249 minus 242 is 7, so we can complete that. We know that 3,311 people do not have the disease or are disease negative, and we know the specificity is 0.92, so that's a probability of testing negative given one is disease negative. So we multiply that 0.92 times 3311, and we get 3046. 3311 minus 3046 is 265. So then we just add these up to get the totals, and everything has to equal. Like the sum of these has to equal 3,560. The sum of these two has to equal 3,560, and these two have to sum up to 507. So just check your work. Make sure that everything adds up. All right. Now I'm going to go over some probability axioms. I'm going to show you how to calculate the PPV, and then what I'm going to do is that's all that you're required to know. I'm going to continue though and provide a formula for the PPV, which can be used in an extra credit for the exam. So if you like this, you can do it for extra credit. If you don't like it, you can wait, and you'll learn it in graduate school. Okay, so that's just an option, that part. But let's go on with the mandatory stuff. Just something about probabilities. Probabilities range from 0 to 1. The probability of an event, it's the likelihood that an event will occur. What's the likelihood an event will occur? Like if you flip a coin, I can calculate the probability of a head or a tails, right? So the probabilities of a heads is 0.5, probability of a tails is 0.1, right? So you can't go below 0 and you can't go above 1. Mutually exclusive means that two events cannot occur together. So you can't have a heads and a tails at the same time. The probabilities of all possible mutually exclusive events in a sample space. So the sample space is the space of all possible events. So in flipping a coin, you can only have two possible events, heads and tails. So that's your sample space. They're mutually exclusive because they cannot occur together. If you add them up, they have to add 1. So 0.5 plus 0.5 is 1. So if we consider P the probability of success, then 1 minus P would be the probability of failure, right? So if we're flipping a coin and heads is a success and tails is a failure, so 1 minus 0.5 is 0.5. So that's how you get those. So those are just things that you have to know. So in our case, what's the probability that one does not have the disease? Well, you can only have the disease or you don't have the disease. probability having the disease is 0.07. We calculated that previously, so 1 minus 0.07 is 0.93. All right, the positive predictive value, by definition, is the probability of being disease positive given your test positive. So what's the PPV for the R test? Well, let's go to our table here. So it's conditioned on one testing positive. If you look at the definition, there's a condition here. It's conditioned on testing positive. So when we talk about conditions, we eliminate everything else from the table. In fact, we only are interested in these folks right here, because these are the people who tested positive. We don't care about the people who test negative. So among these individuals, these 507 individuals, what's the probability of being disease positive? Well, 242 of those 507 were disease positive. So that's how we calculate the PPV. It's 2, let me say 2, oh, but it should be 242. Let me fix that. 242. 242 out of, make sure I got everything else. Yeah, out of the 507. So let me make sure I calculated that correctly, okay? So I'm going to redo that really quick here. 242 divided by 507. Yes. Oh, okay. 0.477. Okay. Or 0.477.48. Okay, so that's how you calculate your PPV. Now notice that this value is not that large. We saw the sensitivity was 0.97, but PPV is 0.477. This varies a lot. The higher the prevalence of the disease, the higher the PPV. So in general, when we're deciding about screening for diseases, we want to screen for high prevalence diseases because we want the PPV to be higher. The lower the prevalence of a disease, the lower the PPV, so it makes it less worthwhile to actually test for, or to actually calculate the test, to do the test, conduct the test. Because testing, obviously, as we know with coronavirus, costs money. So if the PPV is low, and then I should do that for the coronavirus. Now, I've done it before. I have videos showing where I calculated it. If the PPV is very low, then we shouldn't spend money, unless we have an emergency, like now, conducting testing. So there's two factors that influence the PPV. This is something you should know. There's two factors that influence the PPV. One is the disease prevalence, and the other is the test specificity, not sensitivity, the test specificity. So let me repeat that. Two factors influence the PPV. One is the disease prevalence, and the second is the specificity. All right, so now let's talk about so now at this point, right now, you know what you have what you need in order to complete the exam. So if you're not interested in learning more, you can stop here. But for those of you who are interested, I'm going to continue going on. This is good stuff. I wouldn't do it if it wasn't good stuff, but you don't have to do this. But on the extra credit, you will have an opportunity to gain more points doing this. So let's continue with some definitions related to probability. Independence means that information about the occurrence of one event has no bearing on the occurrence of the other event. Okay, so like for instance, if two individuals take an exam and they're not cheating, how one person scores on the exam will have no bearing on how the other person scores on their exam. But if they are cheating, then they're not independent, right? So what happens to one individual will influence what happens to the other individual. So if person A is cheating, then person B is probably going to get the same score as A does. So that's what we mean by independence. So the occurrence of one event will have no effect on the occurrence of the other event. Okay. But if the occurrence of one event has an impact on the occurrence of the other event, they are not independent. Okay, so let's write this out. Now, you'll notice I have these superscripts here. This is kind of working up to my example. So the probability, for instance, that person A gets an A on the exam and person B gets an A on the exam is the product of the two, right? So this is first, we're just doing some little notation. This is actually known as the multiplication rule. And in probability, anytime you see the word and, right, you know that you're going to be multiplying. So and means multiplication in probability. So this is the probability of the two occurring, right? So we can actually rewrite this as the probability of A occurring, or A, in this case A gets an A and B gets an A, is the probability that A gets an A given that B got an A. So this would be the condition, right? Times the probability that B got an A on the test. So it's person B, right? So this is the multiplication rule. And we can rewrite this, like I can calculate the probability that A gets an A given that B gets an A by just dividing both sides by the probability that B gets an A, and then I can just rewrite this however I want. We know we have independence if these two are equal. So the only difference between each side of the equal sign is that there's no condition here, right? So that means that the impact of B's performance on the test does not influence A's performance on the test because we don't see that condition here. So we know we have independence if the probability that A got an A on the test given that B got an A on the test times the probability that B got an A on the test is equal to just the product of the two probabilities. That's all you need to know. Okay? Okay, so Dr. Rodriguez suspects some funny business is afloat in his course. He's concerned about two students, student A and B. Students A and B are both taking PHLT 913, obviously a fake course. The probability that student A gets an A in EPI is 0.8. That's right, I forgot why I did that, because our course is 319. The probability that A gets an A is 0.8. The probability student B gets an A is 0.7. If the probability that student A and student B both get A's is 0.5, are the two outcomes independent? Okay, so I gave you this is the probability student A and student B gets an A. So theirs is 0.5, right? So this is equivalent to right here, right? Because A gets an A and B gets an A, we have that value is 0.5. All right, but we're going to plug this into the equation right here, right? And then we're going to see if it equals 0.5, which you'll see that it doesn't. So the probability that A gets an A and B gets an A is this probability that A gets an A given that B gets an A times the probability that B gets an A. Well, this is the only information we have. So we have 0.8 and 0.7. If we multiply those together, we get 0.56, but that's not equal to 0.5. So that's not equal to the product of the two probabilities. So they should be equal, right? But they're not. So that means they are not independent and cheating is probably occurring. All right, let's use this multiplication rule now and calculate the sensitivity of the test. So we know that the formula or the equation for the sensitivity of the test, or the way we write it out is the probability of testing positive given one is disease positive. We know that's a conditional probability. Now I can use what I know about the multiplication rule here, like in this case, here's a multiplication rule, right? And I want to get this conditional probability here, right? And that's all I do is rewrite the equation. So if I was interested in getting, for instance, probability that A gets an A given that B gets an A, I would divide this side by the probability that B gets an A, and I'd divide this side here by the probability that B gets an A, because then it would cancel out here. What I'd be left is that this conditional probability that A gets an A given B gets an A is equal to this joint probability divided by the probability that B gets an A. And I kind of get that here, right? So I get the probability of testing positive given one is disease positive is equal to their joint probability divided by the probability of being disease positive. So I have these values. Okay, so what's the probability of testing positive and being disease positive? So let's go to our table here. So this is, well, 242 individuals both tested positive and were disease positive. And there were a total of 3,560 individuals. That's 242 out of 3,560. So that's the probability of, where am I? Here it is. The probability of testing positive and being disease positive. Now we already know that the prevalence of the disease, probability of being disease positive is 0.07. So I just divide these out and I get 0.97, which equals to what we found, or what we had earlier, right? Didn't I say that the sensitivity was 0.97? Yeah, right here. So there we just confirmed that. All right, let's calculate using the multiplication rule the specificity of our test for disease D. So specificity is probability of testing negative divided by being disease negative. So here we have their joint occurrence, right? So it's the probability of testing negative and being disease negative divided by the probability of being disease negative. So let's see where these two intersect. So probability of testing negative and being disease negative. They intersect right here. If you're disease negative and you test negative, there's 3,046 out of 3,560 individuals. And where am I? I'm right here. And we know that the probability of being disease negative, well, it's a complement of being disease positive. If the probability of being disease positive is 7%, so it's 1 minus 7% is 93%. So it's 0.8556 divided by 0.93, or this is equal to 0.92, which we already derived before. So that's, or we knew before that that's our specificity. So we've confirmed that. All right, let's continue. Now, the PPV, positive predictive value of a test, can be calculated using Bayes' theorem. Bayes' theorem. You should, again, you know, if you're listening to me now, that means you're interested in this. So this is a very interesting theory, and there's a whole Bayesian type of statistics that we don't really have time to get into here, but it's extremely interesting. But this theorem is very helpful. And it just says that the probability, in this case, of testing, of being disease positive, given that one test, they should be test positive here. Oops. Let me just fix that somehow. Testing positive is, again, we have the intersection of these two events divided by the probability of testing positive. So it must have been like in a hurry here, huh? All right. Now this, as it turns out, this denominator here will be the total probability of testing positive. And if you look at the, so again, like I said, you must be interested in this if you're listening, because I don't want to, if you're not interested and you're ready for the exam, you don't have to stay. But the total probability of testing positive includes those who are disease positive and test positive, and those as well as those who are disease negative and test positive, right? So these are false positive because you're disease negative but you test positive. That's a false positive. So this is the total probability of testing positive. But it includes two parts to it, and this is important when I expand out the probability of testing positive. So you have the probability of so actually this is interesting. You'll notice that there's a union sign here, right? Union means or, which also translates to addition. So the total probability of testing positive includes both testing positive and being disease positive, which I just showed you on the table. So you can do it that way, or you can do it by testing positive and being disease negative. So there's two different ways one can test positive. You can test positive being disease positive, and you can test positive being disease negative, right? So either of these two can occur. So that's why we have the or symbol here. So this translates to an addition. So we rewrite this to equal the following. So this is the total probability of testing positive. So it's the probability of testing positive given one is disease positive times the probability of being disease positive plus the probability of testing positive given one is disease negative. This is your false positive rate times the probability of being disease negative. So let's write this in plain English and then calculate our PPV. So this is what I just mentioned a moment ago. So this is just writing it out in these conditional and probability language. Total probability is the denominator. Well, this first piece right here, testing positive given one is disease positive, is the test sensitivity. The second is the prevalence. So it's sensitivity times prevalence. That's repeated down here, right? This is exactly the same. So sensitivity times prevalence. This last piece I mentioned, this is the false positive rate, and this is the probability of testing negative. So we need the false positive, and we need the probability of testing negative. Well, we know that's 1 minus the disease prevalence, which is 0.07 here, so it's 1 minus that. So this is the one that you might not know how to do. This is the only last piece here. Well, let's start filling things in. So we got 0.97, we know that's the sensitivity, we know the prevalence is 0.07, we repeat it down here, 0.97 times 0.07. So how do you calculate the false positive? Let's go back up here. So being a true negative and a false positive are mutually exclusive. Those are the only two possibilities you can have if you're disease negative. So if you're disease negative, either you can test negative or you can test positive. So these two are complements. So 1 minus the specificity would give you the false positive rate. Let me repeat that. 1 minus the specificity would give you the false positive rate. So this then is 1 minus the specificity. I'm sorry, this is 1 minus the specificity because specificity was 0.92, so it's 1 minus 0.92. And then this 1 minus the prevalence, we know the prevalence is 0.07, so 1 minus 0.07 is 0.93. So what I get here is 0.48, or actually 0.477, so it would be the same as what we got before. So we replicated what we found. Good stuff, everybody. If you have any questions, post them. Have a nice day.